just very quickly, what does missing information mean? I mean, it means what it says, and the idea that we can't necessarily know everything about a physical system is hopefully familiar to anyone who's taken quantum mechanics, but that's not really exactly what we're focused on here. You've been dealing with missing information at one level or another all week. So the really simple example is anytime we have a measurement error, we are missing some information, namely we don't know what the true value of that thing we tried to measure was. And I mention this not to make myself sound like an idiot, but because the way that we deal with that is the way that we deal with all missing information ultimately. If we don't know something, we parameterize it and we marginalize over it. So that's the end of the lecture. You've seen a bit of this also in the context of hierarchical models. They tend to be full of things that we don't know. One of them was that example of, what is the true value of something if you have a measurement that isn't perfect. And as you start building multi-level models, you just add more and more of these things that you don't know. Maybe you have some prior information on them, but there is information which is missing. So, key messages in case you get lost later on, which I would totally understand. As Adam sort of alluded to, no data set probably is perfectly complete, and it's especially true in astronomy, where we are sadly stuck here on planet Earth, and all we get to do is look at the sky and see what we can see, right? Our job as people who work on data is to know whether that incompleteness matters for what we're trying to do. And if it does matter, it is our job to model it appropriately and marginalize over the stuff that we don't know. So, before jumping into it, there's a couple of terms that you will almost certainly hear if you work on survey data, and so we should know what they mean. Malmquist bias and Edington bias. So, fairly quickly. Malmquist bias means, what it says in the picture, if you have a flux-limited survey, that means as you go farther and farther away from us, your flux limit corresponds to a larger and larger limiting luminosity for whatever sources you're looking at. And so if you very naively take an average luminosity, say for those sources, what you're getting is not the average of everything which is actually out there in the full volume that you'd like to look at. Because at the largest distances that you can see, you can only find the very brightest things that are there. So the difference between this naive average and this true average would be called the Malmquist bias. Edington bias is somewhat similar, but it refers to when we are trying to infer the number of sources, whatever the sources are, as a function of luminosity. So generically, fairly generically, a luminosity function like that would be a steeply falling function. There are many more faint things than bright things usually. And so if you have a steeply falling luminosity function and you start perturbing individual luminosities, even with a symmetric measurement error, there's a net shifting upwards of the number of sources to higher luminosities, higher measured inferred luminosities. Here's a cartoon. Okay, cartoons are nice, right? So made up a bunch of data, luminosity on the y-axis and nothing important on the x-axis. There's a lot more of them that are faint than are bright. And if I just put a symmetric error bar onto these things, something which is sort of like square root of L, so it's Poisson-like, then if you do some counting, you will see that more things scatter from below the line to above than from above the line to below, simply because there's a lot more things down here for that to happen to. If you look at it in histogram space, then here, again for totally fictional data, the blue histogram is something that I made up, and then I took all of the points that went into it, and I shifted them a little bit symmetrically up or down, and then made a histogram out of all of the things that appeared above some, say, detection threshold here. And in all of these bins, every single one of them, we are systematically overestimating the number of sources that should live there if we just naively interpret the data that we have. That's the Edington bias. However, those things will not be on the test because they are just particular manifestations of something more general that you could call selection effects, selection being how do things in the universe wind up in my data set. And so the way that we're going to deal with these is in a more general framework. But before that again, let's talk about two more bits of terminology this time on the statistics side rather than the astronomy side. And just to be clear, even though there are two of them, there isn't a one-to-one correspondence with the two things that we just talked about. So censoring in statistics means that a given data point, and here data point means, in our case, a source, maybe a galaxy or a star, a given data point is definitely known to exist, but there's some potential measurement for it which either hasn't been made or isn't good in some way. So we're looking at all the stars in a globular cluster, say, and we've measured all of their optical brightnesses, but we wanted to get all of the radio brightnesses, but for some reason or another, we weren't able to observe all of them. It also is used to describe the situation where you try to get that second measurement, but you don't detect the object, and then people would say, maybe we have an upper limit. Number 2 case is truncation. This is subtly but fundamentally different. Here, it is not just that there are individual measurements for data points that are missing. There are measurements that are missing, and the result of that is that the entire source does not make it into our data set at all. We don't know that it's there. So this comes up very naturally in surveys because you're scanning the sky, and if something isn't bright enough for you to see it as an object, you don't know that it's there, right? So if you're trying to infer something about a population, and you're systematically missing part of that population, you find yourself in trouble. That's truncation. Okay, so there's not a whole lot that can be said in full generality about this, other than where I started, which is that you already know how to do it. And obviously that's not very helpful. So we're going to look at a specific example. Just to be clear, the rest of this lecture is not applicable everywhere, but it's reasonably generic. And by reasonably generic, I mean we're going to be fitting a line yet again. But okay, so here's the situation. LSST will do a galaxy cluster survey. I'm sticking with what I know. So it finds clusters. Doesn't really matter how it finds clusters. We'll find them as places where there are lots of red galaxies, but it could be the sum of red light in an aperture as you scan along or anything like that. And the number that we find as a function of richness is not actually interesting to us. What we care about from a cosmology point of view is the number as a function of mass. Those two things are not the same thing. But fortunately, we expect there to be something like a power law relationship between richness and mass. And so if you take the log of everything, then say the log richness y as a function of log mass x would be a linear relationship. Hence the line fitting. So, didn't quite get that. This is an inference problem that we haven't done before this week. Class, what is the very first thing that you do when I hand you an inference problem? Draw the PGM, right, that's not what I heard, but okay. Good, we can remember 2 days ago. But before drawing it, I'm gonna just say what my generative model is, and let's not worry about selection effects yet. We'll sketch out what it is for the full problem where we have a complete data set, and then we'll add selection effects, and then you can hate me for the rest of your lives. So my generative model will include a mass function. So there are some cosmological parameters, which I'm just going to call omega. And these tell me, as a function of omega, what is the number of clusters that should exist as a function of mass, x. I can think about that if I want to, and I would encourage you to do this, as in our model, omega tells me a total number of clusters and a probability distribution of x for those clusters. So what else do we need? Sorry, total number will be capital N. A richness mass scaling relation, meaning slope, intercept, intrinsic scatter. We will just call those things theta. True values of mass for every cluster x, true values of richness for every cluster y, and data, so measured values of x and measured values of y for every cluster. So far, we're assuming that we have all of that. We don't have to do this, but we're going to make our lives slightly easier and just assume that those measurements are independent. And we know what the error bars are, so that part is taken care of. So with that, let's draw the PGM. I'm not going to make you do it. It's pretty similar to what you have seen several times this week, because this is not the first time that we fit a line this week. But just to go through it quickly, this is a hierarchical model, by the way. It's one example of these. So we have n clusters. They all have a true x and a true y. They all have a measured x and a measured y. The prior for x depends on hyperparameters omega. The true y values follow from x and its own set of hyperparameters theta. And the one kind of funny thing here, which we haven't seen before, is I've decided that capital N is also data. That's the size of my data table. And this is actually predicted by the cosmological model. In fact, I'm going to go ahead and say that in this model, capital N is a Poisson draw from some expectation that omega will predict for me. And again, so far, we're pretending that we know what it is. So, throwing in some qualitatively reasonable estimates for parameters, because we already know something. Here's a mock data set that I generated using my generative model. Every little point here is a pretend galaxy cluster. This is measured x versus measured y. So what I've done is taken some exponentially falling distribution of x's, made up a really big number for the total that I would have, perturbed them to get a measured x, gone back to the true x, figured out where on the line I am to get a average y. That average y is perturbed by intrinsic scatter to get the true y for the cluster, and then that's perturbed again by measurement error. And then we have a point in this diagram. Does that make sense? Okay, slate motions up and down, good. Okay, so I'm claiming again, this is an inference that you already know how to solve based on this week. So here is the likelihood that corresponds to this thing. Counting for the moment capital N to be data, which will not be true later on. There's this Poisson distribution for n, given some expectation from cosmology out front. That's kind of new. But other than that, it's something that we have done before, which is apparently not fitting in one line. But it's almost fitting. So product over all of our data points, there's a p of x given stuff, given its prior, p of true y given its prior and x, and then measured y given true y, measured x given true x. That's the only thing missing there. So this is by now totally familiar, and we're all happy with it, right? Or are there questions? Because if there are questions on this, we should not let them fester. Okay, so before getting into the really hard stuff, quick question for you to put your head together with, along with the person next to you. How would we adjust the generative model that I just described for the case where some of our clusters have measurements of y but not of x? And would that be different if we had measurements of y but only in quotes upper limits on x? Take 60 seconds and talk this over. Okay. Even if we're not done, let's start coming back. I don't want fully baked ideas here. I want half-baked ideas. That's fine. So I'm assuming this is the easiest thing to have up when we talk about this. So half-baked ideas, anybody? Yo.
For the second
Mhm.
question, you could have some sort of like binary hyperparameter that accounted for whether or not there was an upper limit on X, so that if you were trying to like generate data, you could account for how many of them should be in that camp of having an upper limit.
Interesting. Okay. That's, I mean, I'm not criticizing. Uh, I'm just trying to think how that follows through to the likelihood function. That's okay. That's good. I mean, we have a fraction of an answer to a question that you have no business being able to answer, not having seen the lecture yet. So it's good. Anybody else? Yeah.
I was just thinking because the data is only dependent on y, you could still use those values of y to constrain the distribution
Mm-hmm.
that data is being sampled from, even if you don't know how it informs other parts of the problem.
I think, again, we're collectively on the right track. So, okay, I'm going to, what were the questions actually? Some clusters have measurements of y, but not of x. Okay, so I'm going to claim, basically there's nothing that we have to change other than literally some clusters don't have a data point here. So we don't know what this is. This thing, x, is still part of the model. It still has a prior here, and because we know y, there will end up being some constraint on it, given that, well, assuming that other parameters are constrained by other data points, if that makes sense. Now, in terms of generating data, yes, you would have to have some decision procedure for, is this one of those clusters that has x or not? That's absolutely true. To the second part, what if we have an upper limit? I have a question in response to myself, I guess, which is, what is an upper limit? Have we talked about upper limits this week at all? No, because in Bayesian analysis, an upper limit is not a thing. We don't get upper limits out of analysis, right? We get posterior distributions. We also don't get answers out of analysis other than posterior distributions. So if you have an upper limit, probably it means that you were looking at a paper and somebody said, here's an upper limit on this thing, which means they didn't do their job, right? Now, if that's the case, you might have to, you might have no choice, but, sorry, but to assume that corresponds to, some flat posterior and then sort of tails off to 0. I mean, you might be stuck there. But in principle, if you have access to the raw data and the ability to come up with a posterior for x or y or whatever it is, then one need never think about upper limits, right? We have a whole distribution and whatever information that has in it. Yeah.
I thought someone said that you can't stick a posterior in there.
So one has to be careful about exactly what we mean. But apart from that, yes, basically. So I forget who it was that said that. I guess it was Ruth, maybe. Basically, if someone had done their independent analysis and just said this is x at the end of it, yes, they had a prior, and we would need to make sure. So if we were going to plug in their distribution at the end of this, we want to have this prior instead. We just need to know what their prior was, and we can divide that back out before applying ours. It's a mathematically reasonable thing to do. Much more often, in a situation like that, person A, whose work we're using, assumed a uniform prior, and then it's kind of trivial to divide out a constant. But yes, thank you for reminding us. Good point. So as convincing or not as it was, the claim I was going to make is that this censoring issue that statisticians who are not astronomers talk about quite a lot, if we're working in Bayesian land, this is actually pretty straightforward and doesn't require a 60-minute lecture to go over. But feel free to challenge me on that later on. In any case, the example that I want to work through involves truncation rather than censoring, because we're talking about doing survey science. So, in practice, although in the most cartoonish way possible, the sample that we would actually have from this experiment includes only sources whose measured values of their response y exceed some kind of detection threshold. So we're imagining that somebody else has actually looked at the survey data, run a detection algorithm on it, decided that we need to be above this threshold to have a very high probability of anything that we find not being a false association or detection, and then they give us this catalog of blue points. And everything in gray down here, I know about it because I made up these data, but in practice we have no idea what's down there. So that includes capital N, the total number of things. All we know is what I'm going to call N det, the number of blue points that we have. Okay, so another quick brainstorm, just to see what ideas there are at the start here. How would you go about doing an inference of the kind that we want, which I'll remind you includes fitting a line to these things with a scatter and also constraining some parameters for the underlying distribution along the x-axis? How would you go about doing that based on only the data that we can see here? And secondarily, if you didn't care about the distribution in x, would that make any difference? 90 seconds. Put your heads together. We will see the answer later. All right, let's come back. I'm just curious what ideas there are. And if you're worried about sounding silly, let me just say any ideas that you've had, I guarantee you there is a paper out there where someone did it and thought that they were doing the right thing. So anything. Oh, we're still afraid? Oh, so go ahead.
I just wanted to ask, should we know what this cutoff, like, are we?
Oh yeah, we know what the threshold is. That's not a problem. I mean, we can infer that even if we didn't know. Yeah. Yeah.
We came up with the idea that it seems like for x greater than 2, we have a complete distribution, so you could just throw away the data left of that.
Yeah. I'm not sure that would be totally safe, but that's definitely, I mean, it is true, at least for this problem, if we had, if we could do something like this, and we were actually complete above a threshold in the x-axis, then we would be unbiased at least. I don't know if the remaining data would be helpful to us. But then we could constrain the y versus x scaling. Whether you could constrain the distribution as a function of x is a different question then as well. And that is not a fully general thing. That is for a linear problem as well. Okay. We don't have time for me to go down a list of things that people thought were right that would get around this that aren't. But we will go through the correct answer. Okay. But needless to say, simply fitting a line, like minimizing chi-square, doesn't work. And I think visually you can probably imagine why, because you saw the previous plot where you saw that the actual underlying scaling relation was this, and if we fit these points, we're definitely going to get something like that. And likewise, just using the likelihood function that we saw up here before, which is pretty close to just fitting a line, is not going to work. Okay, so how do we do it? Let's see. I think it's most useful to continue thinking about generative models and continue thinking about, in our brains or on our computers, generating the complete data set, but then incorporating the selection procedure into that. So we generate a complete data set, generate mock measurements, and then those things that didn't meet our threshold magically go away to produce a truncated mock data set. So we need to add some stuff to the model. I already mentioned ndet. That's just the number of things that wind up being called a detection. We can allow there to be additional parameters that have something to do with the probability of detection. In this little cartoon, it's maybe the threshold is the only one, and we're going to say that we know it, so this is kind of trivial, but in general it can be there. And we're going to add to each source a binary indicator variable, which is 0 if the thing winds up not being detected, and 1 if it does get detected. And we will call it I for some reason. I think because it has to do with the word inclusion, but I'm not sure. Okay, so here on the right-hand side is a new PGM, and the left-hand side is the old PGM. So what's different? One difference here is that the total number of thingies in the universe is now in a single circle because it's not data, we don't observe it, but it's still a parameter. That's relatively straightforward. We've just added these detection-related parameters phi in case they exist. So those things combined with the measured or potentially measured value of y determine whether something is detected, which is this guy, 1 or 0. And then just for completeness, ndet I've put up here, that would be the number of IKs that are 1. Any questions about the picture? Yes.
I'm just confused why IK is data, because you don't know if you have a 0, you don't know it's out there, right?
That's true. If we have a 0, we don't know anything. But in the generating the universe on our computer situation, we know everything. So it's the same PGM applies regardless. Put it this way, for in the real data set, we do know this, it's always 1, right? So it's a little bit shaky, and I will repeat again, I said it on Tuesday, the PGM is not a perfect tool. But I'm going to claim that we should call this data just because because it's known for the real data, put it that way. Maybe that's the best explanation. Other questions? Okay, let's just continue working with this and see how much sense it makes. Okay, I've already said this, but maybe it's worth repeating. So n total is no longer observed. We added maybe some additional parameters that have to do with detection. Those things combine with the y hat, and here y hat, again, it is a little bit weird, but for those clusters where we have a detection, this is a measurement in the normal way. For those clusters where we don't have a detection, we need to start thinking about this and this as potential measurements rather than measurements that we actually have on our computer. But at least in the case of something like a flux, which I guess this isn't in this example, but imagining this were a flux, you still, in a survey, there is still a measurement, there's still a sampling distribution in the sense that when you look at that particular part of the sky, there is still some Poisson draw for the number of photons that you get, right? Even if it doesn't wind up being added to your catalog. So there's still sort of this double circle in that way. And what else? And NDET is there, okay. So the likelihood for this no longer fits on one line. But it breaks down in this way, and we'll just go through the different pieces. So this term, this P of detected clusters, this is almost exactly where we started. It's still product over clusters, now just the detected ones, of P of X, P of Y, P of Y hat, P of X hat. Don't know why the order came out that way. And all that's been added is this extra thing that says this source had to be detected. So in the simple case where we have a threshold, and if y hat is above it, we detect it below, this would be just a step function, very simple. It would actually be equal to 1 for all of the clusters that are detected, but at least in principle, this thing is now here. For the missing clusters, again, things are not fitting onto the screen. For the missing clusters, let's just see what we're missing. All right. I'll go back, but I remember what isn't fitting on the line. Ooh, there we go. Looks ugly, but it works. Okay, it's similar. We have a product, and now it's over the clusters that we didn't see. So you can imagine that actually evaluating this in practice might be a little difficult, but it will work out. So product over clusters. You've got all of those same terms. Now there's this P of detection equals 0, which makes sense. And the only real distinction is because there aren't measured values, x hat and y hat, that we have. Those are things that we don't know. And when there's something that we don't know, we marginalize over it, right? So we can put this integral over x hat and y hat there. And the reason for doing that is that if we do the marginalization here, all of a sudden, because there's no data for these clusters, nothing distinguishes any of the terms in this product. It's just whatever this is, and this is something that in principle we can evaluate. It's this number to the power n minus n det, which is convenient. And then finally, there's the worst part, which is this combinatoric term that I snuck in there. N total, choose n det. I really, really, really hate this thing. I'm going to be totally honest with you. I don't like it. It absolutely needs to be there. I guarantee you that it's correct. But the explanation that I'm about to give you is one that I can kind of accept as long as I don't think about it too hard. So I suggest that you don't think about it too hard. Well, I'll say the words, but this is something that I constantly go around and around in circles on myself. So there is this concept of exchangeability, which means sort of a priori equivalence of data points, which is something which is sort of generic in the case that we are looking at a class of objects like we're doing here. We don't normally think about it. So what that boils down to is we are analyzing a catalog. The order of lines in that catalog means nothing to us, right? They're all, you can shift them around, they're functionally equivalent. So from a generative standpoint, the number of ways that I might randomly produce a functionally equivalent catalog, in this case, where we have detected things and non-detected things, is proportional to that. Now, we've never worried about this kind of thing before, but before we didn't have a free parameter in whatever the combinatoric term was. So here we can't get away with throwing it out. And that is the claim that I'm going to make for why this needs to be here. However, if you don't believe that, in a couple of minutes, I will sketch out a completely independent derivation which gets you to the same place and might be more intuitive, and is the reason that I believe this is correct. Before that, though, I'm just going to say we can simplify things down a bit more. So if the PDF associated with the total number is Poisson, which I claimed it was for this experiment, and when you have sources that just sort of come into existence in the universe, that's probably a decent approximation much of the time. It turns out you can marginalize that out analytically, exercise for the reader. If you want, I can point you to a paper that does it, which means ultimately the big old likelihood that we had in that PGM turns into just what we were doing before times a couple of extra terms, with just a couple of more things that we need to calculate. Namely, we need to be able to calculate from the model an expectation value for the total number of clusters and an expectation value for the total number that we should detect. So it's a little bit more work, but if we have such a model that we're trying to constrain, these are things that we can calculate. And if we understand the selection process. If we don't understand the selection process, we're hosed anyway. So a little bit of extra work, but not actually that much more complicated, is sort of the bottom line. So here it is. If you didn't believe me or didn't follow some of that stuff, here's what I would suggest you do. And this can be done on paper, 1 or 2 pages of paper, depending on how large you write. Let's think about this from a less Bayesian, more maximum likelihood perspective. And just think about modeling the detected data only, so we're not augmenting the data with all of these missing clusters and then magically getting rid of them through marginalization. We've just got our little plot of y hat and x hat, and there's lots of clusters sort of in this region. And that's it. Now think about taking the space, here's the threshold, and chopping it up into lots of little delta x hat, delta y hat squares. And in each one of these, we're going to have a Poisson likelihood. So the data are number of things that we found there, and the model will predict number that we should find there, or a mean value for the number that we should find there. And then there's a Poisson likelihood. Intuitive? Okay, so do that. And now take the limit where these things become infinitesimally small. So in that limit, we have either 0 or 1 actual detections in each cluster. That produces a simplification. If you work that through, I promise, you will get to the same simplified expression for the likelihood, except for a factor of n det factorial, which is a constant. And so we don't care. So if you have time, let's say you can't sleep tonight because this is bothering you, then you can work through this. Or maybe you're taking a plane back to your home and the TV isn't working or whatever. Okay, so one more question for you all. I think this is one that helps build a little bit of intuition, at least it did for me. Think about, with your neighbor, what information do we get from this point? I mean, it's kind of obvious, as somebody pointed out. If we're all the way over here, where we're detecting basically everything, we pretty much understand the information that we get from these things. It's what we usually think about. But over here, what information do we get from this using a model that knows about the truncation mechanism and knows about at least the shape, roughly, of the underlying distribution as a function of x that isn't there if we do something simple like minimizing chi-square? In other words, why is it worth doing this, and how does this get us the right answer, whereas just fitting a line doesn't? Couple of minutes. Go. All right, I know people are still talking. Let's try and pool what you have talked about a little bit for efficiency, because that's how it works. Any ideas, even if they're not fully formed? Who's brave enough to yell out? This one I am going to wait until there's an answer, by the way. Okay.
Okay, half-baked idea. If we don't model the selection effect at all and don't know anything about or model anything about the lower points, and we just fit a line to this thing, then that data point will be sort of heavily contributing to like making the slope of that line shallower because it'll like pull it up in that end.
Yeah.
But if we understand something about sort of the underlying distribution in like X or whatever, we have an understanding that that data point itself is actually a pretty large outlier from the relation. So that's maybe telling you something about the maximum uncertainty on given data points or the average uncertainty or something like that. But we can actually probably account for that by the fact that we know how far away it is from the center of the distribution.
Good. Anyone want to add anything? That was like 90% of the way there. Yep.
We said it gives us some information on like the values that X might have overall, because like clearly we're observing something with those X values over there, so it informs us that like where things might lie in the parameter space. But like for the same reason we were hesitant to trust the information it might provide because it seems like it is an outlier overall.
Okay. Also good. I should say I have in mind for this problem that we do have some prior information on the distribution of X. We at least know that it's a steeply falling function. So the existence of things at low values of X on its own probably isn't surprising. But good contributions both. Here's what I think. So yes, certainly if we just fit a line to the blue data, horrible things happen. If we try and do something sort of in between where we say, okay, I know that I couldn't possibly have in my data set something below this line. So I'm just going to say change my model for the sampling distribution such that if there is a, if the true model goes like this, then anything at this value of X, I'm just going to have sort of like the tail of a Gaussian instead of a whole Gaussian who's centered here. That doesn't actually give us any new information. Basically, we're saying anything in my data set has to be above this line. This thing is above the line. Tautology, right? At least in the case of models that are near the truth, we know that the average down here then is very, very small compared to the threshold. So anything which is detected had better be right above the line, and it is. And so there's nothing new added there. But if our model also includes roughly the shape of the distribution as a function of X and the total number, then we would know, for example, let's say we're looking at something near the true model. The average value of Y for these things is way down here, but there's 10 to the 4 of them. And so one of them scattering X sigma away from the line and being detected, that is information. There's one of them here, not 0, and not 100. So it's giving us in a very degenerate way information about the total number, about the shape of the mass function, the size of the intrinsic scatter, and the slope and intercept of the line. Put enough of those together, and with enough stuff up here as well, and you can constrain a model like this. However, any intuition that we have built up over the years about how well we can constrain line fits given a certain number of data points, all of that becomes very, very shaky. And so I urge you, anytime you see a problem like this, go through the whole procedure of simulating data and analyzing it to see how well you actually could do in principle. Because the fact is, we're leaning, that whole explanation that I gave you, that leans pretty heavily on prior knowledge of the shape of the mass function, at least how steep it is roughly, and that sort of thing. So in some sense, we lean very heavily on priors in this kind of situation. And knowing when how many data points do you need to get into the regime where the data are telling you the answer and not the prior, that's something that I don't know how to give you a general answer to without saying just go and simulate it and do it. So that's one takeaway. I didn't put the figure in here, but one can go ahead and actually fit these data the right way and the wrong way, and it's many tens of sigma wrong that you will be if you just try and fit the blue points. This is also sort of maximally bad in terms of the situation for trying to fit a line. Okay, just a couple of final things to say here, going back away from the specific example. A question that you are probably asking yourself now, and I would totally understand, is, do I really have to care? I mean, this was a maximally bad example, but I'm working on something else. Do I have to care? That can be answered in principle. So in general, selection effects are ignorable, meaning you don't have to care. If these two things are simultaneously true, first, the priors on parameters that you care about, and any of those additional parameters that might exist that have to do with selection only are independent. I don't know if that's true in your case. It might be. Often we can just construct them to be that way. But here's the one that kills us for surveys. You would need selection to not depend on potentially unobserved data. And in the case that one of your data points is the thing that lets you know that a source exists, that's just not going to be satisfied. If you were interested in totally unrelated quantities to that, meaning intrinsically there's not a correlation between them, and in the measurement there's no correlation between them, then you would still be okay. But that isn't very often the case. Those two conditions, by the way, they didn't come from nowhere. It basically comes down to mathematically asking, what do you need for the posterior distribution on the parameters of interest to not involve phi? And you can, if you stare at equations for long enough, convince yourself of that. But I'm not going to do it here. There's a less mathematically strict version of the same question, which is now the one in your minds, which is, okay, maybe ignoring things selection isn't exactly right, but is it wrong enough that I have to care about it? And that isn't something that I can answer necessarily. But again, you can go through the procedure of mocking up a data set that has the selection you think is there, and then analyzing it in a way that doesn't account for that. And you can see if you are biased by 0.1 of your final error bar at the end, then go ahead and write the paper and publish because nobody cares. And if you're wrong by 1 error or 10, then you probably should do a little bit more work. Okay, this is not the exercise that we're going to do, but just to mention at the bottom of the lecture notes, there's the invitation to think about what happens qualitatively when you have data that are missing according to other mechanisms, like, I believe this is completely at random. This is a cut on the x-axis, like we mentioned, and this is a cut on if we have y1 and y2 as a function of x, this is a cut on y1, where y1 is not completely independent of y2. So those are things to think about if you want. Otherwise, we have the actual problem here. There's a couple of things that I want to say before we launch into it. One of them is sort of trivial. So first of all, there's this warning at the top about making a copy and working in the copy. That's just general good Git advice. If you don't follow it, that's fine. But the problems to be solved look a little bit different in this case. So at the very top, you see this block which you should execute. And then where there is code for you to fill in, you'll see a construction like this with a try. And what we try to do is read it in a solution file. And if we don't find it, then we do code which is actually in the block. The reason for all this is if you are just clicking through and don't realize that there's something to be filled in there, then you will see an error. And if you go to the bottom of the traceback, it will actually tell you the reason for the error is you didn't put in the solution. So what should you do when you see this? You should go up here. You should delete all of that junk, and then do what it says in capital letters, and then you will be fine. So it's a little bit more work for you. The advantage is even in the future when I make changes to this notebook, I can guarantee you that this thing will work if you put in a correct solution, because I have the solution file, and so I can just run all the cells and see that it produces something and doesn't throw some kind of crazy error. So anyway, I hope that isn't too much additional overhead for you all. The other comment to make, I guess, is that most of the code in this entire problem is given to you. I've only withheld the things that actually specifically have to do with coping with missing information. So really it just boils down to writing down the likelihood function for that piece, well, for the particular situation which is outlined here. And if you run into trouble with that, I think eventually I will actually push solutions. I threatened not to earlier, but we'll add those. But during this hour or whatever it is when you're working, I would encourage you to just come up to, we'll put the board up, and you can talk to each other and scribble and maybe ask for help. And that might be the best way of going about it. That's all I have to say. All right, folks, let's quickly look at solutions, I guess. So earlier on, I gave you this PGM, which I believe is right. This is at least one way of writing it down that explicitly breaks the successes and failures into different plates. Is this clear to everyone? Okay. At the very last minute, I also added this additional hint, which is just a mathematically true expression. So for the successes, the probability of success given only T0 and Ts, which is the thing that you would want to plug into the grid-based posterior calculation that I gave you, is the integral of the temperature of that launch of the probability of success given T0, Ts, and temperature, which is the very first thing that you coded up. But all right, so let's quickly go down here and shout where you see one of those try except blocks. Okay, so the first one is just implementing a function. I think we can probably skip that. In fact, many of these are sort of just places where I didn't want to assume what you would like to choose for things like priors. So for example, I just chose a uniform prior, which you probably shouldn't do in general. You should use your brains a little bit, but that's what I did. What else? For the range of temperatures, Tmin and Tmax, I just chose the minimum and maximum temperature that were in the original data set, I think, which is very silly. Oh, okay, so I guess I really shouldn't have done that because I'm not supposed to know what these things are, but I'm imagining somebody just told me, sorry, we lost the data, but I remember they were between 54 and 81 or whatever it was. It doesn't matter too much what you choose for this. I guess it would matter if it was actually smaller than the correct range, but beyond that, it doesn't necessarily. That's the wrong notebook. Okay, but as you all found out, 99.9% of this whole notebook is in writing the likelihood function. So let's look at that. So here it is. There's two parts corresponding to these two plates. This doesn't show up because that's the prior. So for the failures, what is it? In the log, we sum over the failures, and it's just 1 minus p success of the temperatures, which we know, given T0 and Ts. Is that part clear? That's the intuitive part. For the successes, we're missing the one piece of information that would distinguish them. So in the end, we're going to have one thing that we have to calculate, and we're going to have it to the n success power in the posterior, so multiplying by that in the log. And the thing inside the log then is what I wrote down here, the integral of this function that you coded up over the temperature within the range that it's allowed to be in. And I guess I can't remember if I said you had the freedom to choose what this distribution was or whether it was assumed to be uniform. I assumed that it was uniform. And so this integral is the integral of the logistic function between two bounds that we decided. And if you go to Wikipedia, it will tell you what that is, minus this Jacobian term in front. And so if you code up that thing, it has a log in it also, but it's just this expression. So if we do that, in fact, I should run this notebook. Let me do that. Run all, and then we can actually look at what the output is. Okay, where were we? We were here at the likelihood. So then we, in quotes, do the fit, which all I've done is evaluate the posterior over a grid. You can fill in, this is just filling in the function call for whatever the syntax of the function that you wrote was for the likelihood. These are the, oh, let's get rid of this, sorry. These are the very rough two-dimensional posterior constraints that it comes up with. And in case you haven't seen this before, this is not what you should do in practice. This is just a quick and dirty thing. But if we rely on the central limit theorem, which we probably shouldn't do in this case with a few tens of data points, then approximately speaking, looking for delta log posteriors of these specific numbers in 2 dimensions gives you the correct credible regions. So we're not going to pretend that this is real, but it shows you the shape of the posterior at least. And you can see there's some kind of constraint on those 2 parameters. That's all we're really looking for. These are the 2 1D posteriors. So if we're thinking as a function of temperature, you're likely to fail, and then there's a transition, and you're likely to succeed. That transition is in the 60s, according to this model. And the width of that transition is something like 5 degrees. We then go and look at what is the failure probability as a function of temperature, and that's what it is according to the fit. Was there a question? Yeah, okay. And at least for me, this is when I realized that the model that I suggested for you is actually a really terrible idea, because that model is forced to go to 0 at some point. And in the original plot, all the way at the top, it's not obvious that the probability of success ever goes to 0, really, because you've got these things here where there are a lot of successes and this guy here. So maybe a 3-parameter model with a, what is the level that you have, even in the best case, would have been a better fit. But for an exercise, it's okay. So then the final piece was to do all of that again, but without the censoring impacting the data. And there, the likelihood is the simpler thing. So the failure part is the same. The success part is just the corresponding thing, where we just multiply p success given the known temperatures for all of the successful launches. And so here we are. And then the really weird thing, which again, I'm pretty sure follows from the fact that this is not a good model, is that the new constraints, when we have all of the information, are actually worse. So those are the red dashed lines. They're shifted a tiny bit, which at least it makes sense that they're shifted in the center of this logistic function shifts to smaller values. And the width of it shifts to larger values, which really only makes sense if it's trying to not actually, it's trying to not find its way down to 0 probability of failure anywhere. So the data actually know that there's always some probability of failure, basically. And we should have been smarter when choosing the model. So heaven knows what this is telling us. But that is the solution. And that's basically it. If you really, really want to, you can think about what you would do with a truncated case. If you don't know the number of successes even, I'm sure it becomes horrendous. I do know from previous years giving a different version of this problem, there's essentially no missing data mechanism that you can imagine, which is as bad as this. This is just absolutely the worst possible case, and if you have any more information than this, you would probably conclude that launching at low temperature is riskier than launching at reasonable and high temperatures. Any questions? Okay, one very, very final word in 10 seconds. I had up there briefly on the screen this figure, which is one that I didn't include in the lecture notes but could have, which just explicitly shows, so the blue contours on the right there in this triangle plot are what you find if you fit a model that accounts for truncation here, knowing what the form at least of the prior on x is, even if we don't know the parameters of that function. and it does okay. And the red contours there are if you do something fairly sophisticated in terms of linear regression, but not accounting for the truncation. And it gets nice tight constraints, right? But boy, are they wrong. It's just not even remotely close. So this is from a quick note that I threw together this year because I kind of got sick of people publishing red contours. It talks through basically the same stuff as we did today with a little bit more math. I will push an update to the lecture notebook if nobody minds. It has links to this and maybe a couple of other things if anybody is interested in seeing in practice how this works. Definitely not a comprehensive survey of the literature because I don't know of anything outside of galaxy cluster cosmology. Just going to go ahead and say that. But some things to look at if you want to.